So to summarize where we're at, we've defined both a scalar line integral, so line integral of a scalar function along the curve C, and we've defined the vector integral, or the vector line integral along a path C as well. And one of the most important points about these line integrals is that in general they are path dependent. They depend on the path. So we'll kind of write this down. So the line integral of a scalar field we've suitably defined as, the notation for this is just the integral over C of the function phi with respect to arc length is the accumulation of the function phi on the curve C and the line integral of a vector field on a curve C was defined as the integral of f, the dot product of f, some vector along the curve, integrated with respect to arc length. This is the accumulation of the vector field f in the direction of u hat along C. And for a very special case of this, we've seen that and when in most sources when they say line integral, this is what they mean, a line integral of a vector field. Tangent to C. So this is when u hat is chosen to be the unique tangent, or the tangent vector to the curve C. This is the integral of f dot this unit tangent vector, or just simply put f dot dr. And what we're going to do is we're going to kind of investigate this special line integral some more as we kind of move through the lecture. So all of these line integrals in general, important point. In general, line integrals depend on C. The way of writing this is that they are path dependent. But the following example is a very important example because it's going to show that this idea has very important exceptions. So sometimes, for certain types of vector fields, this tangent line integral is actually not going to be path dependent. It'll be what's called independent of path. So what we'll do is we'll consider a mass m moving in a gravitational field close to the surface of a large gravitational body. So for instance, you can think of projectile motion on the surface of the Earth. And for mass moving in this situation, we know that the force on the mass, if we orient ourselves with respect to the ground being at the bottom of our coordinate system, z equals 0, the force on the mass is just going to be pointing downwards, and it'll be of magnitude negative mg, where m is the mass of the body and g is the gravitational constant. Note that this force is a conservative force field. Specifically, the gravitational potential in this approximation becomes negative m times g times z, where z is the height above the ground level. And if you take the gradient of this function, will exactly be equal to this negative mg k hat, or negative mg in the z direction. So we'll see that this is actually a very, very fundamental aspect to this example. But let's consider the work done by this force field along two separate trajectories. In order to do this, we have to we'll define the work. We have to define what the work is for a given vector field, so a given force field, and we can do that in a very, very nice manner. I'll show how to derive that right now. So we'll do this before we get into the example. So for a constant force, call it FC, and a constant displacement, we'll call this DC. The work done by F along the displacement DC, if we say we're moving from A here to B here, we move in a straight line, so we have a constant displacement. This vector is DC, and the force on A, we'll say, is the constant force FC. The work done moving from A to B is exactly equal to the dot product of FC with DC. Or if you'll remember from your basic elementary physics class, work is force times displacement, or force times distance. So this is the amount of energy done, by what I guess you could say against the force field F, or with the force field F, as you move A from B along this straight line path. And you can visualize this in a number of different ways, but perhaps the best way of visualizing this is saying that, well, we know the dot product is the length of F, or the magnitude of force, times the length of DC, cosine the angle between these two vectors, because I guess we can say that this force, I drew it along the displacement, but this constant force doesn't necessarily have to be along this displacement path. So let's make this picture here a little bit more general. basically the force maybe looks like this, or even it could be against or with, it doesn't really matter. This force is the constant force FC, and this is the angle between FC and DC. So we know from our dot product that this is true. And then what this is saying is exactly, well, we know that you can interpret this in two different ways. First off, you can say that the magnitude of force I think the best way of interpreting this is saying that it's the magnitude of force cosine of theta. This is the total amount of force acting along this axis, the projection of the force vector onto this axis, and then it just multiplied by the total distance traveled. Right, so this is the force acting on this mass as it moves in this straight line path, multiplied by the total distance, or the length of this vector dc. So this is essentially why this is true about this dot product. And the idea is that we have to generalize this idea now to a general path moving in a force field that's not necessarily that's not necessarily constant. The force could be changing at every given time. So this is the simple picture, so to speak. In the more complicated scenario is now the scenario where we're moving from point A to point B along some possibly very complicated path, and for every single point on the path the force might be pointing in a different direction. And also have a different, very, very large or very, very small magnitude depending on the force field that we're moving through. So initially this seems like possibly a very complicated thing, but well, we can just define this curve as the curve C. And we know that for any curve C, we can parameterize it and get the tangent vector, t hat, the tangent vector field to the curve at every given point. And then it shouldn't take too long to see that the total amount of work done is going to be related to this idea. The work done moving from A to B is going to be exactly equal to the line integral over C from A to B of the force field, which the force in this case, this is the case of constant force and constant displacement. This is the more general case of non-constant force field. F of R. And also, a possibly very complicated path. We'll parameterize this by R of t. So it shouldn't be hard to see here that the work done moving from A to B is going to be based on this idea, but really it's going to be the line integral of the force field dotted with the unit tangent vector, or the line integral of this force field along the curve C, because this is just F dot the unit tangent vector ds, the line integral of F dot t hat ds along the curve. the accumulation of all of these components, these dot products, give us the total net work done. I guess saying net work here should be, more specific. But this is exactly the same thing as just saying integrating with this local function at every single given point. So which is exactly what we're doing when we end up defining the line integral. Right? Because if you think about it, this right here in the constant case is the same thing as f dot d hat multiplied by the length of d. And that's exactly what this magnitude of f cosine theta is. It's f dot product with d hat times the length of d. So the idea here is that we're just integrating this component at every single different point along this curve, and the total net work done moving from a to b is this line integral. This is how we define the work. We say that the work done by if it's a force field, this is going to be exactly this line integral. So back to the example, when we consider this example right here, we'll consider the work done to move a mass m in a gravitational field over two separate paths. So we'll consider the following two paths. And these will be relatively simple paths. And we'll also treat the points as relatively simple as well, just to simplify calculations as much as possible. So we'll say we'll go from the point 0, 0, 1 is our coordinate system. So it'll be the x-axis and the z-axis, to the point 1, 0, 0. And we'll just consider the straight line path, which is the curve z is equal to 1 minus x. And then we have the same points right here, 0, 0, 1 and 1, 0, 0. And instead of considering the straight line path for path 2, we need a different path. So we'll consider the path z is equal to 1 minus x squared, which looks like this. Now, both of these paths are paths that go from, say, a point A to a point B, the same point. And both of these paths are, we're assuming, are immersed in the same constant force field right here. But in general, right, this, depending on the example, F could be more complicated. But we're just kind of trying to illustrate something here. So we in general expect, because we have two separate paths, we expect this line integral to be different, or the line integral giving us the work to be different. So for path 1, right, we'll first start by parameterizing the curve, which you always want to do. In this case, our curve, z equals 1 minus x, is the same thing as, we'll choose x equals t for our parameter, and 0, and then z is going to be 1 minus t. And this is valid for t from 0 to 1. This correctly parameterizes this curve. And for our curve r of t, or a parameterization of the curve on path 2, we'll also choose t for x. So x is t, y is 0, and the z coordinate will be 1 minus t squared. And this is also valid for t from 0 to 1. And this example is nice because f is relatively simple, right? It's just the constant vector field. So f on the curve, f at r of t, is going to be equal to 0, 0, negative mg. And same thing for path 2 as well. F at r of t is equal to 0, 0, negative mg. Note that in general, f is a function of position, right? It's a vector field, so it could be much more complicated. It's just going to involve plugging in the parameterization of the curve into the function itself. That's what this f of r of t is saying. So if we continue onwards, and now that we have the vector field r of t, and we have the curve r of t parameterized, and we have f of r of t, we can go through and evaluate the work, or the line integral for work. I guess before we go through and do that, we know that in that line integral we're going to need the expression for r prime as well. So let's go through and calculate that first. It's always nice to stay organized and do that. This will be derivative of this with respect to the parameter, which is 1, 0, negative 1. And then r prime for this curve is going to be 1, 0. And the derivative of this function will be 2 times 1 minus t times negative 1 from the chain rule. It will be 1, 0, negative 2 times 1 minus t. So then the work is the line integral of f dot dr, which as we've seen simplifies to the line integral, in this case from 0 to 1, the normal integral from 0 to 1 of f of r of t dot product with r prime of t dt. And you remember that if you use the standard definition for the tangent vector up here in this equation right here, so the tangent vector here, the ds is the magnitude of r prime, t hat is r prime, the vector divided by the magnitude of r prime, so those cancel out, and this reduces to just this formula right here. So when we go through then and calculate the work for path 1, the work done against the vector field f along path 1, this becomes the integral from 0 to 1 and of the dot product of this vector with this vector, which will be 1 times 0 plus 0 times 0 plus negative 1 times mg, which is just mg dt, and this is mg, the integral of 1 dt is equal to t from 1 to 0. So the work done in this case is just m times g. This is the work done on path 1. More specifically, you can think of it as the work done against the vector field f, moving the particle in path 1, along path 1. So for path 2, that this is going to be the integral from 0 to 1, the line integral of this vector field dotted with the tangent vector. That's f of r of t dotted with r prime of t dt. And when we go through and do that, this becomes a little bit more complicated. It's going to be integral from 0 to 1, 1 times 0 plus 0 times 0 is negative 2 mg times 1 minus t. This will be 2 mg times 1 minus t dt. So this is 2 mg. Integral of 1 minus t is going to be t minus t squared over 2. from 1 to 0. This is equal to 2 m times g times 1 minus 1/2. And 1 minus 1/2 is equal to 1/2. This is just equal to mg. We get that the total work done against f going along path 2 is also equal to mg. So this is an important example, and it really shows us a lot. It shows us that there is a certain class of vector fields for which the line integral, so that this is specifically the line integral tangent to curve C. So this third type of line integral right here is path independent. So it's not always path independent. In general, it's not. But there's a certain class of vector fields that are path independent, and it shouldn't take you long to guess what that class of vector fields are, based on where this force field is coming from. Right? For this example, the force field is coming from a conservative vector field because the force is coming from this potential function right here. And sure enough, this is exactly the condition. Right? For any conservative vector field, we're going to see that the line integral is path independent. This is a very, very important idea because this example is relatively simple, but we'll be able to show this for any conservative vector field, no matter how complicated it is. So I encourage you to do this example out again for another path. Specifically, try the path z is equal to 1 minus x cubed. Right? You'll get the exact same thing. You'll get the work along this path is still equal to mg, which is a very convincing argument for this example. So we want to try to investigate a little bit more clearly, what's going on here in this example. And it's a really important observation because this is going to essentially define when the line integral is path independent, and not only that, it's going to give us an alternative way of classifying conservative vector fields. So first, what we'll do is we'll investigate path independence. So suppose we have a vector field F, and two separate paths connecting points R and Q. The picture here looks like you have R, you have Q, you'll have some path C1, call it, and some path C2. So path independence means that for any path C1 and C2 connecting any 2 points R and Q, if the vector field is path independent, means that the line integral of f dot dr, and like I said before, typically when we say line integral, and when you hear line integral, it means the line integral with respect to the tangent vector, the tangent field on this curve. The line integral of f dot dr over c1 is equal to c2, the line integral of f dot dr over c2. And it's very important to point out that this is the same, right, equation as the line integral over c1 of f minus the line integral over c2 of f being equal to 0, which we can rewrite using our simplifications of line integrals. This is the same thing as the line integral over c1 of f plus the line integral over c2 traversed in the opposite direction of f which is the same thing as the closed curve line integral over the union of these two paths, so the union of c1 and the union of c2 traversed in the opposite direction. So it's this closed line integral being equal to 0. Or if we call C the curve C1 union opposite direction C2, right, then path independence, which says that the line integral along any path has to be equal to one another, no matter what path you take to traverse R to Q. It's the same thing as saying the line integral along a closed curve C, composed by found by taking the union of C1 and negative C2. C is a closed curve of f is going to be equal to 0. Or the circulation over this closed curve is going to be 0. So it's actually relatively straightforward and easy to show the inverse of this statement, which is very, very nice. And the inverse of this statement is that, so this statement that we've just shown is that if the line integral of a function f is path independent, then the line integral along any two curves has to be equal, which means that the line integral over the closed curve, right, that you get by traversing the first curve, this first curve once, this is in this direction, and then traversing the second curve in the negative direction. And that's this, right, our C here is equal to C1 union C2. So that if a line integral is path independent, then for any two paths, the line integral has to be 0 over the closed curve that you get by forming the union of those two paths. We can also show the inverse of this statement very, very nicely, and that's that if the line integral is equal to 0 along any closed curve C, then the general line integral of f along C1 is equal to the line integral of f along C2 for any C1 and C2. I recommend you go through and try and show that. It's relatively straightforward. It just involves, being able to find, for a given C1 and C2, being able to express that C1 and C2 as a closed curve, which we've already kind of talked about right here. So this is really nice, though. Essentially, we've established now everything we need to go through and show something very, very nice about vector fields, specifically about conservative vector fields. So we'll first summarize this theorem as, we've shown that if, or the line integral of f dot dr is independent of path, if and only if the line integral along any closed curve C is equal to 0. Right, so remember, if and only if is a by implication. It means we can go back and forth from either of these two statements. So the idea here, though, is that with this theorem, we have everything that we need to go through and show something really nice about what a conservative vector field must obey. And this theorem is the following. It's if f is a conservative vector field in some domain D, then the line integral of f dot dr is path independent. And we can show this by kind of breaking it up into a couple of different steps. And it's important to also note here that f in all of these fields have to be nice enough to apply the steps that we're going to apply. In this case, f must be continuous. But the idea here is that, and we'll go through the proof right here. If we assume that f is conservative on D, that means there exists a function phi such that the potential function f is equal to the gradient of phi. And so if we now consider the line integral over some path C of f dot dr, we know that if we evaluate this over the curve C, where say it's parameterized by, this is the point R, which is the position vector at A, position vector at B, it's the point Q, and then any one of these other points is R of t, and this line integral is going to be the integral from A to B of f at R of t dotted with dr, which is just R prime of t dt. And we haven't used the conservative assumption yet, so the conservative, if f is conservative, that means that this is going to be the integral from A to B of f of R of t, which is going to be the gradient of this scalar potential function evaluated right at the point R of t, because that's the vector field, and it's dot product with R prime of t dt. And this is the same thing as the integral from A to B of the gradient phi dotted with R prime of t, where the gradient of phi here is being measured at the point R of t. So I don't need to rewrite this. We can just keep this here. That's what this is saying right here. But what you should do now, right, is think of how we can simplify this. What the best way of rewriting this is going to be. And what you should do is remember how we define the directional derivative, or the if you were to take, say, the derivative, the t derivative of the function phi of R of t. So either think of the directional derivative or the chain rule. But from the chain rule, right, our chain rule applied to this composition of functions says that the derivative, the t derivative of phi of R of t, the scalar function phi on a curve R of t, is going to be exactly the gradient of phi evaluated on the curve R of t dot product with the derivative of R of t, R prime of t. So what we have inside this expression is exactly just the t derivative of the composition of phi of the scalar potential at the point R of t. And it's the integral of this derivative with respect to time, which is the same thing as the integral from phi of the potential at A to the potential at B of the function d phi, where phi is the, this is what happens when you make the change of variables here. So this just becomes the difference phi of B minus phi of A. And since this phi has to be a differentiable function in order for f to be a continuous vector field that's equal to the gradient of phi, that means that when if you evaluate this on a closed path, so this is just on an open path, and this alone is very interesting because this alone is telling you that the line integral of any conservative vector field, no matter how complicated it is, if it's conservative, the line integral will always reduce on the line integral of tangent to the curve C will always reduce to just the difference of the scalar potential at the endpoints of the curve. So that's what this is telling us. It's for any conservative field. And I guess to be exact here, I put phi of B, phi of A, but we really wanted to note this as phi of R of B minus phi of R of A. which is just saying the value of the potential function at the point Q, which is the endpoint of the curve, minus the potential function at the point R. But this is really nice because it's essentially giving us this path independence. And the continuity assumption here is very important because right, if C is a closed curve, so R at A is equal to R at B, right, that means that the line integral over C of f dot dr, remember this is for the still in this theorem proof where f is a conservative vector field, this is equal to phi at q minus phi at r. But this is a continuous function, so phi of q minus phi of r is equal to 0 because q and r are the same points. And this ends our proof right here. So this is really nice, and essentially what we've shown is the following two things, which I'll summarize. We've shown that if f is conservative, then the line integral of f dot dr is path independent. And we've also shown that path independence of a given line integral this is an if-then statement, so I want to emphasize here that f being conservative on some domain implies path independence, and path independence of a given line integral is the same thing as that line integral being equal to 0 along any closed curve C. Now, it's important to note here that 1 actually is a by implication, and we will see that any path independent or any vector field for which the line integral is path independent in a given domain is also going to be conservative. So you can move backwards, but for now we haven't proven this. So this is just where we're at in terms of implications and what we can use. But even this is enough to write down, say, the converse, the logical converse of 1. The converse of statement 1 would be that if the line integral of f dot dr is not path independent, then f is not conservative. This would be one way of checking to see whether the line integral along a given path is conservative or not. Alright, so if you can find, say, two paths for which the path integral is different, then the function f equal, the vector field f is definitely not going to be conservative. And I will write up here, I'll write the fact that this is in fact a by implication. So let's go through and quickly prove this statement right now. So we'll prove the theorem that if f is path independent, or if if the line integral tangent to the curve C is path independent, then f itself must be conservative.